you can hear me, right? Right, fine. Uh, so what I've done is to put up a brief introduction to some of the terms that you will be looking at or hearing about in virtual screening. And there's a PDF file called vsbrief.pdf. That's basically posted on Slack. And I would suggest that you take the next 5 or 10 minutes to just go through it quickly. And you don't have to remember every term in it, but at least just have an idea of the terms that you're going to be seeing in the next few slides and so on. So we kind of catch up in 10. Yeah. And announcements. Okay. We'll push them there. Yeah. And also, how many of you are now kind of familiar with all the Unix commands? Not good enough? Okay. How many, could you just raise your hands if you're still not very familiar with Linux commands, then Unix commands? Not familiar. Please, just even. Um, yeah, because you're going to be coming across a fairly new set of instructions that you haven't done before, or certainly not seen yesterday. So in any case, don't worry, we will help you through. And also, how many of you have worked with PDB files? Protein data bank files. So PDB, all of you? Okay. How many of you have worked with Smiles files? Okay, Smiles just one. Have you heard of Smiles ever before? Yes. Okay, great. That's great. Okay, and how about PDB-QT? You can put your hand down. I think I'm pretty familiar with most of it. Okay. So these are some of the formats, file formats that you will be coming across and having to work with. And also the instructions that you will find in the tutorial are fairly straightforward. But there will be occasions outside of the tutorial that you might have to do some text editing. And when I say text editor, please do not use Microsoft Word. Okay, Microsoft Word is not a text editor. Use Notepad, Sublime, or any other file editor or text editor. And that's pretty much it. And we kind of start at 10. So take the next 5 minutes to just go through the PDF file. And if you have any, if you need any clarifications, just let me know. Yeah, PS brief, yeah.
Need it.
Yeah, okay.
Hello, hello. Okay. For the people in the room, please add yourself to the channel lecture materials. If you don't know how to find the channel, go to the Slack and click on Add Channel or Browse Channels, and you're going to see a new channel called Lecture Materials. Please do that. Otherwise, we have to add you one by one. Thank you very much.
Thank you. Right, so it's kind of bang on 10. Okay, so this is basically something which we started a couple of years back, courtesy a COVID competition. We didn't win anything in the competition, but the output was still Drug Sniffer. Just recently got published. Oh. Yep. Can you hear me now? Good. Right, I'll just restart for those who didn't hear me previously. We started this process of building Drug Sniffer a couple of years back. And it all started because we were part of a competition to identify drugs for COVID. Unfortunately, we did create drugs, but none of them were active. In any case, the pipeline that you're going to be using today is pretty effective when it works. And the idea behind Drug Sniffer is to provide you with a platform where almost all of the actions that you will need to be performing on an individual basis can be completely automated. Now, it performs two tasks, combines both what is known as ligand-based virtual screening as well as receptor-based virtual screening. Some of those I'll discuss in the slides that I'll present later on. And to kind of give you a general idea of the drug sniffer approach, Amit has already given you a fairly brief overview of the process. So it essentially has 7 steps. The first 2 steps are not part of the pipeline, even though it's shown there. This is simply because all of you will have different ways of preparing your protein, and the protein preparation task and the task of identifying pockets in the receptor are much more challenging and cannot be easily automated. And for those reasons, those 2 will be explained separately, and you will go through a brief tutorial on how to do it using Chimera X. The rest of the parts will be I'll take you through stepwise, and you will be performing those calculations on your consoles, as in you'll have to log in to the server and perform those commands. So how many of you have done virtual screening before? Barring Travis Wheeler's lab. No one? Just one, okay. And David Holly, yes. Okay, so as you can see, here are the first 6 steps that you are seeing on the screen. So as Amit mentioned, If you're particularly interested in kind of finding a drug for a given target, the goal, of course, is to find out which target and also find a suitable structure for the protein that you're going to be building a drug molecule for. Thank you. And this process will be described by Amit later on. The second step, as I mentioned earlier also, is that you will be identifying binding pockets. These are potential sites where the ligands can bind. And this step also cannot be automated. There are softwares that can do it, but the efficacy of these softwares is still questionable. And we now come to the de novo design part. Right. How many of you understand the word de novo? Simply put, de novo means from scratch. So you're going to build something right from the basics and then build it up. And this is a fairly common way of doing drug design if and when you have little or no idea of what kind of ligand is going to fit the binding pocket. So on the left, you see a simple protein for which I've already identified the potential binding sites, which appear as atom or spheres in different colors. And given these binding sites, as I mentioned, you have two ways to go about trying to identify a drug. The first case, let's assume you do not have any idea of what the ligand should look like. You can then, of course, resort to de novo design, which is what we will be doing in a couple of minutes. And then under this umbrella, you can actually perform either deep learning methods. That's something we're not doing. And the one which I'll be focusing is on evolutionary algorithms. Has anybody worked with evolutionary algorithms or heard about evolutionary algorithms? No one? Okay. I'll take you through those steps as well. The second one, now the top one is, of course, what we call receptor-based virtual screening, or at least the first part of it. Second part, which is also part of drug sniffer, is when you do have a set of ligands that are known to bind to a given protein. So then the goal or the challenge is, can we identify other similar ligands based on the concept that highly similar ligands are likely to have similar properties or similar binding affinities? The other option is to go for what is known as a pharmacophore query. Now, this basically means you have a general idea of what the ligand looks like, and you can actually define regions where there are electrostatic charges or electrostatic parts of the molecule, a hydrophobic end, and so on and so forth. So it's basically a geometrical arrangement of the portions of the ligand that you would like to see. And you can then use this as a template and search for ligands that are likely to follow this pattern. Now, pharmacophore methods are fairly good when you have a generally good idea of what the ligand should look like. If you are running blind, please do not use it. And there are methods, of course, which will help you automate the process of identifying or calculating pharmacophores given a series of ligands that you may have in your list. Otherwise, it is better to actually get a trained medicinal chemist to define the pharmaco for you. It's much easier that way. We won't be doing much of pharmacophores today, unfortunately. We won't be doing much of pharmacophores today. Yes. So as Travis once pointed out, it is basically to try and identify a geometrical arrangement of the patterns in the molecule that you're looking for. So it could be a hydrophobic end on one side, electrostatics on other, and so on and so forth. So having identified these kind of locations where you would like a certain set or type of atoms to be present, you can mark those positions and then use that as a template, query a large database of ligands. Is that clear? Right. So as I mentioned, de novo essentially means you're building something from scratch. And how many of you have played with Lego? Sweet. Or if you haven't played, have you seen Lego? Great. So de novo is pretty much like playing with Lego bricks. The only thing you need to consider is how do I arrange it, make molecule that looks sensible. Now, as you can see on the left, I can arrange those bricks in various different ways. And you can get odd shapes. And that's the same thing if you were to try and do it naively using bricks that kind of represent atoms or fragments. Now, you can also tell the computer to do the same. But in order to do that, you have to tell the computer how two bricks connect. Without which, you're basically going to end up creating a molecule which may not be synthesizable in the first place, may not even work, or may not be even suitable for the purpose you have in mind. So this is, again, as I mentioned, Lego. So here you have just a series of small atoms which I have kind of merged into or morphed into bricks. And these bricks can be joined, as I mentioned, in various different ways. But you need to make sure that these structures are actually synthesizable. So in order to do that, you can actually define which fragment can be connected to which fragment. And by doing so, you can create a series of rules that prohibit connections that should not ideally be allowed. Or vice versa, you could basically say, I will only allow fragment A to bind with fragment B or connect to fragment B, but B will not be allowed to bind with C. So having constructed these kind of series of rules, you should be able to create a molecule that makes sense, but you at present would probably be able to only create one or two. So let's get the computer to do the same. But while doing so, you need to consider a few things. First is, of course, as I mentioned, synthesis. You cannot take any random molecule to an organic chemist and ask him to synthesize. A typical synthesis would cost you around $300, euros, somewhere in that region. And this is when you actually do it in bulk. So if you have 1,000 molecules, none of which are synthesizable, you are pretty much spending 300,000 euros or dollars for doing nothing. The other thing is, of course, how much does it cost to make the molecule? As I said, $300 is kind of an average value. It can go much higher, simply because the number of reaction steps involved in creating the molecule, that is starting from your basic reagents and all the building blocks that you have to the endpoint, will vary according to the number of synthesis steps involved. So how many of you have had a background in organic chemistry? None. Oh, no. One. Two, okay. Now there are tools online that will, given a molecule, tell you how to synthesize it. It's called retrosynthesis. But they only work for cases where there is a well-determined procedure. There are also methods in using artificial intelligence that can tell you how to synthesize, go about synthesizing the molecule. But then again, these are all expensive, and you probably need a good, healthy subscription to get those accessible. Then comes the more important bit. Assuming you've taken care of the first step, which is synthesizability, the second, which is more important than the rest, is binding affinity. Is the drug or the drug molecule that you've created, does it have a binding affinity that is of any use? So for a typical drug, we expect that the binding affinity should be 100 nanomolar or less. It becomes less interesting if it exceeds that value. And then comes the ADMET. How many of you have done any ADMET studies before? 3, good. Now, ADMET, as it stands, is absorption, distribution, metabolism, excretion, and toxicity. Now, when it comes to many of the ADMET papers, they generally focus on the last one, which is toxicity. But all the other 4 are actually equally important. Does anyone have an idea of why absorption should be important? This doesn't matter whether you're making a small molecule drug or. So in terms of absorption, you're basically looking for something known as bioavailability. How much of the drug is actually available in the system? And therefore, how is it easily absorbed by the system? And that means us. The second one is distribution. Has anyone heard of blood-brain barrier? So it's a key thing that not all drugs need to cross the BBB, or the blood-brain barrier. Some drugs do. Do you know which kind of drugs might be required to cross the BBB? Any? Oh, sorry. Neurodrugs, yes. It's a very simple thing. It does need to cross the BBB, otherwise it's not going to be effective. And then, of course, metabolism. How quickly does the drug get metabolized in your system? Does it produce metabolites that can be toxic? And excretion. How quickly does it exit the system? And how and where? And toxicity. Now, toxicity comes in various different forms. The primary one is liver toxicity. And as you go on further in the pipeline, I'll introduce you to some of the other toxicity models that have been created specifically for ADMET. And then, of course, there is this thing called pan-assay interference compounds. Now, are you aware that ligands can be promiscuous? Which means that you have a target receptor A, which is for which you have created the drug, but there's a good chance that the drug can also bind to protein target B or C and so on. And this is something that needs to be avoided, especially if you want to avoid side effects. Now, you can actually detect while you are creating the molecule or the drug, whether that is likely. And that is usually because there are some certain fragments that cause assays to give you binding affinities where none should exist. Or in any case, you should exclude those compounds. So all these things have to be considered when you're trying to create a molecule from scratch. It doesn't matter whether you're creating from scratch, let me add that. You should also consider it when you have a list of compounds in your database, excluding the first one. Because if you have a list of compounds in your database, the assumption is it can be made at some point. As Amit pointed out, there are several different databases from which you can extract the compounds to play with. Right. Has everyone heard of Darwin? Darwin. Charles Darwin. Nope. Okay. Well, you've all heard of survival of the fittest, right? So that's pretty much the same principle that applies when it comes to evolutionary algorithms. You start here with a population of molecules, which you can create using various different ways, as I mentioned, the Legos. And having created that population, you need to first understand what is fitness. Now, fitness could be basically a figure of merit that you attach to every molecule to kind of say how good is this molecule for the given task. And that could be a binding affinity, or it could be a toxicity prediction, and so on. And so in your population of, let's say, 100 molecules, you have to calculate 100 fitness values. You can then suitably rank them and then decide, I'm going to create a mating pool where selected individuals from this population are going to enter, and they are going to go through a process of crossover and mutation. Everyone familiar with crossover and mutation? Yes? And this cycle repeats itself for as long as your computer allows, or you run out of patience. Now, this is a very simplistic scheme, but if you were to implement it computationally, it's a significant challenge. Part of the challenge lies in the fact that as you iterate, you are going to produce molecules which seem suitable, but it also has a tendency to stagnate. And when I say stagnate, it means that the fitness values do not improve. So you get a plateau. And this is a scenario that occurs quite often with de novo design, at least when you use evolutionary methods. Now, I mentioned you do have your building blocks, or basically the fragments. Now, what you want to do is to try and create molecules from these fragments. But how do you go about it? You can either say, I'm going to have strict rules on what can connect to what, or you can use what is known as synthesis schemes. So these are well-established reactions which allow you to kind of say, A reacts with B using this reaction scheme, and the output is this. So in the software that you will use later on, there is a scheme that is implemented that allows for this. The only thing you need to remember is that the reaction scheme is going to produce a lot of molecules, only a subset of which are likely to have any useful activity. It doesn't mean that the entire space of synthesizable structures is druggable or drug-like. Right. Now comes the filters. Now, when you keep building, or if you keep on building or adding Lego blocks, you're probably going to create a mountain. And if your pocket is only of a size of this, there's a high likelihood you're not going to be able to fit the structure inside the pocket. So of course, you can then decide, do I want a filter based on the number of atoms, filter based on the molecular weight, or on in terms of the hydrogen bond donors, hydrogen bond acceptors, and so on. And more importantly, the lipophilicity of the drug. Is everyone familiar with lipophilicity? Yes? Why would you want lipophilicity in a drug? What does lipophilic mean? Simple. What does lipophilicity mean?
Lipophilicity means how much you can say hydrophobic, means water repelling it is. That's lipophilicity, I think. Because of after the means it has to penetrate in the cell membrane, and it is the cell membrane has lipids in it, so it has to be somewhat lipophilicity, so to cross over the cell membrane.
Yep. So you do need your drugs to kind of have that property of lipophilicity to be able to penetrate the cell wall and then perform the desired action. So it's not like you need a high lipophilicity or a very low lipophilicity. There's a certain range where it is kind of useful. So we have various different rules that have been implemented by authors or people who are interested in this. And this table here is just giving you an idea of the filters that you can apply at various stages to chuck out compounds that are not likely to be useful. And when I say useful, to have some kind of a drug-like behavior. In general, most of the marketable drugs fall in the space of, say, less than 500 Daltons, less than, and a multiple, say, 5 to 10 rotatable bonds at max, and a lipophilicity in the range of 3 to 5. Right. Now I mentioned figure of merit, which is basically the fitness that you need to calculate for each molecule. And typically we're going to use docking because we're going to try and see if the molecule that you have created or designed can actually fit into the binding pocket that you have specified. And the way you do it is to calculate a docking score, which is basically a measure of the binding affinity, or at least it should correlate with binding affinity. But as Amit mentioned, the correlation is often poor. And this is simply because the docking method typically applies approximations. And if you want to get away from those approximations, you'll have to use more and more computational power. And that is at times it's pretty much not possible. So if you want to have a quick and dirty scheme of using docking to get an idea of whether the drug is likely to bind, you can use this approach. Of course, docking can also have layers. So the docking that we will be using is fairly simplistic. We're going to try and do a simple docking to understand whether a drug is actually likely to bind and use that value later on, try and see how well it correlates with the actual activity. Now, when you are doing these fitness evaluations, docking score alone is not going to be enough. There's a high likelihood that many of the compounds will have a similar score. So what else can you use? As I mentioned, you are creating a population of structures. So if you recall 100 structures in the population, how diverse are these structures? Remember that evolution proceeds or sustains itself better when there is diversity. If there's homogeneity, you're going to get a lot of crap. So what you want to do is to try and have a diversity, a significant diversity, which means that you can actually have multiple scaffolds in your population. And when I say scaffolds, it means that these are different chemical entities or basic building blocks around which other fragments can be joined. So the greater the diversity, the longer the evolutionary run can sustain. And then comes the problem of how do you use or reuse the docked data? Has anybody done docking here? No. Students? Just a few. Okay. You will be doing docking a little later, and that is when you will understand the concept of docked poses. But for now, you can think of it as there are different guesses made by the algorithm as to how a certain drug is likely to bind inside the pocket. So you can then use each of these poses or orientations and ask, what is the score for this orientation? Now, the docking program will give you its score, and on top of it, you can add additional scores. And these are some of the scores or routines implemented inside the program that you'll be using. Right, so the software you will be using for de novo design is known as AutoGrow. Now, it has a library of almost 94 chemical reactions, and it also provides you with a fragment library, which is basically your building blocks. And using these 94 reactions, you can create a sizable library of compounds. But as I mentioned, there'll be only a small subset of that library that is likely to behave like a drug. Now, the good thing about AutoGrow, as I mentioned, is that you do not need any prior knowledge about what the drug should look like. All you need is basically an idea of what the binding pocket looks like or where it is located. And the program then tries to create structures that are likely to fit the pocket, gives you a docking score, and then tells you, here is my list of compounds, do what you will. Now, somebody asked about pharmacophore-based screening. Now, the output of the de novo approach would be a huge bunch of structures. Now, to identify what the pharmacophore would look like, you can perform a simple molecular alignment. And you would ideally see hydrophobic ends towards one side, electrostatics towards the other, and so on. Now, this doesn't always happen, and it also depends on how you align the structures. But in general, if the docking program has succeeded in its objective, you should get an idea of what the ligand structure is likely to look like. And based on this, you can now create a pharmacophore definition. And as I mentioned, the pharmacophore definition is not just limited to electrostatics or lipophilic entities. You can also think about hydrophobic, hydrogen bond donors, hydrogen bond acceptors, where are the aromatic rings, and so on. Then all these basically give you a general picture of what the ligand looks like. You don't have a true picture, but at least you have an idea of what the ligand should look like. And using this as a template, you can now search libraries to say, give me compounds that have this kind of a pattern. But as I mentioned also with pharmacophores, you do need to have a significant amount of knowledge of what the ligand should really look like. And this can be done if you were to use de novo approaches, because they come without any knowledge whatsoever and build on that knowledge. And assuming that the objective has been achieved about discovering a drug for the pocket, you can go ahead and use pharmacophore methods. Now, if you are not a medicinal chemist, or if you're not familiar with how to define pharmacophores, there are tools online, something known as Zinc Farmer, which is a web service. So you should be able to upload a simple molecular structure, and it can give you the pharmacophore features that can then be used to do a similarity search in their database. Right, so this part basically now completes the de novo part. I'll move on to the next one, which is similarity searching. Now, as Amit mentioned earlier, you have your protein, you've identified your protein, you have identified the binding pockets, and you have, assuming you have performed a de novo simulation, which has then given you a list of ligands. Now, the list of ligands that you get may not be sufficient. So what you can do is now to say that I will use these sets of ligands and try and see if there are other similar ligands in databases online or wherever. And to do this, you have to understand the concept of molecular similarity. Have you all heard of the phrase, beauty lies in the eye of the beholder? Yes. Similarity is pretty much in similar terms. Right. So the concept of molecular similarity derives from the fact that there is this famous saying. It says similarity in structure also implies similarity of property or similarity of the biological activity. But as I mentioned, similarity is also perceived differently, and it also depends on how you represent your molecule. Now, you might see visually the structure of the molecule as a simple set of atoms and bonds. But for the computer, it's a whole new problem. So when it comes to doing a molecular similarity search, you need to consider three aspects. First, how do you represent the molecule, which makes it amenable for the computer to do a fast search of databases which are significantly huge? Second aspect, how do you measure a similarity? If X is similar to Y, how would you say, is it 90% similar, 80% similar, and so on? So you really need a similarity metric that tells you so. And then, of course, there's a concept of data. So where do you get your data from? Now, similarity, of course, as I mentioned, there are various levels or layers of similarity. Now, there is chemical similarity. So if you look at the top row there, all I have here is for a series of molecules, I have things like molecular weight, lipophilicity, number of rotatable bonds, and so on. And at this level, you could basically say, what is the similarity between two compounds? You could probably argue that it is very similar in terms of the number of rotatable bonds and aromatic rings. But this is basically just simple chemical similarity. The other level of similarity is looking at other features which are not immediately visible to you. And that means you're basically looking at very localized effects. So it could be a small fragment that is very similar or is present in both compounds. And that cannot be easily captured by some standard chemical similarity. So you have to look at the structural features of the compounds. And this then contributes to your molecular similarity. So as I mentioned, data. Amit has already gone through a huge list of data that we compiled for our previous approach. Now, there are experimental databases and there are theoretical databases where you can extract data from. And things like ChemReal, has anybody worked or heard of ChemReal? So ChemReal is basically an experimental database. And it is data curated, contains data curated from literature. Now, that one has somewhere around 2 million structures. And then there's PubChem. Everyone's familiar with PubChem? That one has a lot of data, but not all molecules are drug-like. And then there are structures that are basically created using the computer. So for instance, there is this database called GDB. I have no idea what the expansion is. And that has around 1 billion. And then there are the companies like Enamine, Molport, and MQ, which claim to sell you 5 billion synthesizable structures. But not all of them, again, have that drug-like feature. And the general idea is that you can order a compound and it will be given to you. Of course, you have to pay the money. So if you have these databases, the idea is, let's say you have a compound and you want to identify its nearest neighbors. And when I say nearest neighbors, it's basically saying, how can you identify 10 similar compounds? And the assumption here is that if I find those 10 similar compounds, if my molecule A has a binding affinity of 8, are my nearest neighbors also likely to have a binding affinity of 8 or lower? So let's start by basically saying, here's the molecule that I want to use as my query. I want to then choose a suitable representation that allows me to screen or run through this huge database of billion structures. Use a similarity metric to rank those structures. And then choose, say, 10 or 20 of them for additional analysis. So it could be either for synthesis or for more extensive computational studies. Right. So is everyone familiar with the term substructure? Yes? The substructure very simply means have the molecule, the structure of a molecule, and you're looking at a small part of it, which could be a fragment. The fragment could be just one atom, or it could be a series of atoms. Now, in representing the molecular structure, you could think of an array of numbers where each position in the array indicates whether a particular substructure is present or not. So if I were to take a molecule, has everyone heard of paracetamol? Paracetamol, yes? So if I were to say, is there a methyl group in paracetamol? You could put a 1 there in your array. Okay, okay. And likewise, if you were to say, is there a different aromatic ring present in the structure? If you find it, you put a 1 again. Now, this means that you need to have a database of substructures which you are actually looking for. So if you have a database of substructures or a known set of substructures, you can basically ask the program to indicate the presence or absence of each substructure. And the presence or absence will be then marked as a 1 or 0. And the substructural patterns can include element counts. It can also have atom pairs. But it's typically these ring systems that are of more important. Now, in this setup, you have some standard substructure keys, as we call them. There are some things known as max keys, and that means you have 166 fragments that they are actually looking for in each molecule, which means your array of numbers is going to be 166 bits long. And when I say bits, it's simply because you are marking the presence as 1 and 0. Okay? Now, likewise, you can actually have another fingerprint or substructure key known as PubChem, which extends this length to almost 881 bits. Now, which one works better is something you have to find out on your own. But there are other options as well. Now, as I mentioned here, you do need to have a database of fragments to decide what kind of bit fingerprint you're going to create. The other option is to try a different kind of fingerprint where you do not need any predefined patterns, which means you do not need to have a database of fragments. And you can have more patterns than the limitation imposed by 166 and 881, as you saw in the previous slide. Which means I could basically create an array of 1024 numbers, and each position in this array could be a pattern that I'm looking for. So I could basically look for an atom sequence of CCCC, which is 4 carbons, all connected in a single chain, and so on. Now, I won't go into the algorithm, but the general idea or the message I want to convey through this is that you're not restricted to the patterns that were present in the previous slide. So you can have 1024 bits or 2048 or 16,000 odd numbers, or arrays of 16,000 odd, each then trying to capture a certain pattern that is present in your compound. Then comes, of course, how do you compare two arrays of numbers? Now remember, in most cases, or at least the cases that you'll be working with, these are binary fingerprints. You're going to have just zeros and ones. So if your compounds are represented as a series of zeros and ones, you can use what is known as the Tanimoto coefficient. We call that Tanimoto in chemoinformatics. For computer science scientists, it's called Jacquard index. And I'll explain briefly what the Tanimoto coefficient is. But if your representation of the molecule actually has continuous data, Do you understand continuous data? Instead of zeros and ones, you basically have numbers like 4.5, 3, and so on. In those cases, you can decide, I can calculate a different similarity metric. So for instance, you can calculate a Euclidean distance. Has anyone come across Euclidean distance? Computer scientists, yes. But I can understand this is going to be a bit tricky, but do not worry about this one. But there are several different metrics that you can use to define how similar a compound is to another. The goal is to basically just produce a single number which says I'm X% similar to Y. So Tanimoto similarity is something which is very popularly used when it comes to similarity searching. And on the left, I have a simple example where you have two molecules, M1 and M2, which are represented by the pattern of ones and zeros. So one indicates the presence of a certain fragment. And if that corresponding fragment is not present in M2, it's marked by a 0. Okay? Now, to calculate Tanimoto similarity, you're going to do one thing. First thing is to check how many bits are on. And when you say on, we basically say how many bits have the value of 1 in M1. If you count, you basically have just 3 cases where the value is 1, especially the first, third, and fourth columns for M1. And if you look at M2, you have 4 bits where the value is 1, starting from the second and moving on to the fourth, fifth, and sixth columns. So we basically say there are 3 bits set in A and 4 bits set in B. And what is common between the two molecules, which is to say, how many cases do you find that the bits are set or bits are 1 in both cases? Unfortunately, for this problem, you basically have just 1 bit set. And so you have a value of 1. So I have got A, B, and C. A is the number of bits that are set in M1. B is the number of bits set in M2. And C is the number of bits that are set in M1 and M2. It's an intersection. So now you can go ahead and calculate the Tanimoto similarity between these two compounds, which comes to a simple equation of C divided by A plus B minus C, which is roughly around 0.17. And this Tanimoto coefficient always varies between 0 and 1, where 0 implies no similarity, and 1 implies perfect similarity. Now, you'll be using a tool known as OpenBabel, where you can actually play around with some of these Tanimoto coefficients. Now, I have here a molecule which is represented by CC. Now, this is typically how you would use SMILES, as I mentioned before. SMILES is basically just ASCII text. And you can simply write down ASCII molecular structure in terms of just numbers, the element symbols, and a set of hashtag, a set of symbols, other symbols such as hash, which you will see in the second one. So in the first case, we are basically looking at ethane, which is just CC. And OpenBabel then gives you a different kind of fingerprint, where you would see that there's only 1 bit set, which is on the number 4, whereas everything else is 0. C hash C implies hash implies a triple bond in SMILES notation. So this one is an alkyne, ethyne. And we are going to calculate the Tanimoto similarity between these two compounds, which comes out to be 0. So these are some of the things that you will be looking at. Right. Now, in addition to fingerprints, there are, of course, other ways to compare molecules. Now, what you have seen before is basically just a 2-dimensional representation, which means I just have the structure of the molecule, which is drawn typically using just atoms and bonds, without knowing exactly how they are located in 3-dimensional space. So you can now start doing similarity searches in 3D space as well. But remember, if you go from 2D to 3D, you also have the problem of conformations, which means for every molecule, depending on the flexibility of the structure, you might have to generate that many conformations. So these are two methods. I won't go too much into those. In the first method, which is known as ultra-fast shape recognition, we are going to use something known as moments, which is basically a set of numbers, which is an array of numbers. And we are going to use that as a representation for each molecule. In the second one, has anybody done structural alignment, 3D structural alignment? Yeah. Now, 3D structural alignment can be done in multiple ways. If you think of, has anyone played with Rubik's cubes? Yes. So what you generally do with the Rubik's cube is that you hold one end and try and arrange the pattern on the other side, right? And it's the same thing here. So if you assume that my left hand is the molecule to which I want to align the second one, I can simply rotate the second molecule till there's a maximal overlap of the volumes of those structures. And that is what is being done in the second approach, which means which means you are, so as I mentioned, again, in three-dimensional space, you have two methods. First one being ultra-fast shape recognition, which basically just gives you an array of numbers, and you have to simply compare those numbers. In the second case, you are trying an alignment. So you should be actually able to see which parts of the molecule are superimposed. But remember, all these have to be done in 3 dimensions, and the alignment will change depending on the conformation you're looking at. In the second case, we are going to be looking at fingerprints. Now, as I mentioned, these are the substructure fingerprints, which means you only have 166 bits. And in the second case, you have something known as an extended connectivity fingerprint, or ECFP4 for short. And this has a representation that is 1024 bits long. So just as a test case, I chose 100,000 molecules randomly from a database called Zinc and chose one of the structures as a query. I'm not interested in particular as to whether the structures are being retrieved in the right order or so. I'm simply interested in the time that it takes to do these similarity searches. So given one structure or as a query, I'm going to search the rest of the 99,909 structures and rank them. So can everybody just read the text on the figure? Okay. So this is your substructure search, max, which takes around 250 seconds. So along the y-axis, you have all the methods, and along the x-axis, it's the time taken to search 99,999 or 99,999 similarity calculations, so to speak. And then you have the ultra-fast shape recognition, which is a 3D method. You have Shape It, which is also a 3D method, but this is based on alignment. And the last one, which is ECFP4, is also a fingerprint-based method. Now, you would see that the USR method, which is a 3D method, is slightly faster than the fingerprint-based method. And max basically takes the longest amount of time. But if you look a bit more closely, what you need to understand again is what was the time taken to calculate the conformations. And here I'm only calculating a single conformation. On my machine, which is around 7 years old, takes about 10 seconds to calculate one single conformation for a molecule. So if I had to do this for 100,000, you can do the math. And remember, this is just for a single conformation. Now, if you had to do this analysis repeatedly for all the different conformations that you may find, this method would start to suddenly become infeasible. On the other hand, the fingerprint method, all it requires is that the fingerprints need to be calculated exactly once, and you can store them in a database. But with Max, the reason why the timing is significantly high is that these are substructure fragments. So remember, in ECFP4, there is no limit on the number of patterns that can be found. Whereas with Max, you are looking for specific fragments, and these fragments may be found in multiple locations. And each substructure search does take time. And that is the reason why it has added to the overall time. But in a typical scenario, you would pre-compute these fingerprints and store them in a database. And you could then do a very fast similarity search, in which case the times would be significantly lower. But if you were to calculate them on the fly, you can expect to have timings of this order. Now, the fingerprints that you've so far looked at are just not limited to ECFP4 or substructure fingerprints. There are path-based fingerprints. Now, path-based fingerprints is what you saw with OpenWable or OWable. And then there are some pharmacophore-based fingerprints as well. There are three-dimensional fingerprints as well that have been proposed. And some of the articles suggest that ECFP4, ECFP6 is the best fingerprint to use. But that is a decision that is not easily made. And the reason I would argue that is here you have two molecules, which, as you can see, are slightly different. Right? Can you all see the difference? And if you were to do a similarity search or do a Tanimoto similarity calculation using the path-based fingerprints, you would actually get a similarity of 1. Okay. Now, the problem with this is that it simply says a value of 1. 1 simply says that it is a similarity based on the representation. It does not necessarily mean that the compounds are identical. So there's a difference between similar and identical. Okay? So you will run into issues like this if you were to use fingerprints. Yeah. Now we'll proceed to the tutorial. And for that, I would like you to log into the servers. And then we can start the process. Log into the servers as in log into whatever logins you did yesterday. Has everyone got Chimera installed? Yep. Okay.
Has everyone logged into the Exceed bubble? Raise hand if you haven't logged into the Exceed.
Right, is everyone logged in? No problems logging in? Okay. Now, we're going to be working with a protein called 3VRI. Have a question? Okay. And there's a bit of a write-up about this protein in the tutorial. Okay. And what we're going to be working also with is the ligand that is bound to it, which is abacavir, which is an antiviral drug. And you can basically go to PDB and just type in 3VRI and you should get the same structure. The only difference is I have shown you the full structure in a slightly different form. And we're going to be using drug sniffer to try and model some drug compounds that can potentially bind to this, to the binding pocket in 3VR, right? Now, drug sniffer is basically set up as a pipeline, and the pipeline is implemented as a workflow. And for this workflow, we are using a software called Nextflow. And as Amit and I have pointed out earlier, drug sniffer works in various stages. So for the purposes of this tutorial, we will be performing these stages individually. And later in the evening, you're going to try and apply this pipeline once you have set it up for the protein of interest that you would want to work with. Okay? Does that make sense? So each stage in this pipeline is contained in what's known as a Docker container. And as I mentioned again, that for instance, if you were to do docking, you need the AutoDock software. You also need something for preparing the protein and so on and so forth. So there are several different softwares that need to be downloaded and so on. So what Docker does is basically gives you a container system where all of this is already present, and all you need to do is to download this image. And you can straight away go ahead. What Nextflow allows you is to connect all these stages and go from point A to point D, for instance, without you having to do anything once you've just set it up. So next, for the drug sniffer, if you were to run the entire pipeline, you could simply enter the parameters of your choice. For instance, you could enter the protein on which you want to work, where the pocket is located, and a few other parameters which I'll explain later. And that's all. And you should just simply be able to press run, and you should be, hopefully you'll be done by the end of the day. The other option, which is what I'm going to go through, is each stage. One of the stages is significantly long, so we won't be doing it. We've already done this for you, and we will be giving you those examples to work with. So for some of the others, like the de novo step, which is typically the lengthiest part in this pipeline, those you will have to try and do it on your own. I'll tell you how to do it, but you can do that individually as well, or you can just simply run the pipeline going from start to end. And as I said, that will complete by end of day. So to begin with, Amit here is going to explain some things about this protein. And for this, you will be using Chimera. Okay, so you'll need to know what the binding pocket looks like and so on. And he will be showing you also how to identify potential binding sites for this protein. You already have this ligand abacavir, which is bound to this ligand, but assuming that information is not available, how would you go about trying to identify binding sites in this protein? That is something Amit will explain to you, but those steps you will have to do later on. There is no simple software to do it. Now, in the tutorial, I have given you a program called fpocket. Now, fpocket is not installed on the server as of now, but it is kind of, should I say, a little confusing if you're not very familiar with Unix tools and analysis. So I would suggest you use a standard web server to predict these binding pockets, and then you can decide where you want to start applying the de novo approach. Okay, so Amit.
Thank you. So I'm going to assume that you are seeing a PDV file for the first time, even though I know a lot of you have seen a PDV file before, but it's better to assume that you are seeing it for the first time. Okay, so stop sharing. Yeah. Okay, which one? Has anyone done it? Oh, okay, we have some people. Okay, let's wait. So I'm going to go through the PDV file, and in the meantime, you install it. Okay. Anyway, that actually gives us some time to go over PDB file. So PDB stands for Protein Data Bank. There are 3 mirror sites for it, and we will go to the RCSB site. So in the Protein Data Bank, nowadays it's almost required. If you solve a protein structure, you have to deposit the structure in this data bank. And then the protein that we'll be working with today is 3VRI. So if you, on the right here, if you just type 3VRI, you get the PDB ID. So PDB ID are 4 letters words, and well, 4 character. It can be number and letters. So we'll go to the 3VRI. So that's the protein that we'll be working today. And you can click on the download file and the PDB format, and save. I mean, for me, it says directly to download directory, but you can move it to your favorite directory. And I'm going to move it to our drug sniffer. We are going to look at this. We're going to look at this 3B.
Hi, for the people that have uninstalled Docker by mistake, please install Docker. To do so, run the same command, sudo apt-get, but instead of remove, you're going to write install. Also, please remove docker-engine. Yeah, can you do that? So it's sudo apt-get install docker, docker.io, and so on. The same command as before, just without remove, with install. You have not removed it just yet, right? So I don't know the command myself. Can you write that line and send it to Slack so that he can copy and paste it? So can you navigate to Slack, please? Okay. Yes, can you copy this into your, oh, thank you. Okay,
Yeah,
just copy this with an S.
Yeah, we'll put the S.
So I'm sorry. Oh, I apologize. I should not do this. So if you have removed Docker, please run the following command: sudo apt-get install docker, docker.io container, and run C. You don't have to do it if you have not run the earlier remove command. I apologize for this. Thank you very much.
Thank you. Okay, we should have our Docker back.
Uh, has anybody gone ahead after removing Docker as well? As in, has anybody tried to install Drug Sniffer? Nope. Hopefully not. We've gone ahead.
Okay, so if you have downloaded 3vri.pdb, that's the PDB file. I'm going to quickly look into the PDB file just to show you how the structure look, and then we'll look the structure by Chimera. So make sure you open it with Notepad, TextEdit, anything that's not Microsoft Word. Simple. So in a PDB file, what you have is lots of comments about the experimental condition, crystallographic symbol, and so on, and then the secondary structure. But the part that we are interested in, and I'll go directly to that part, is whenever the leftmost column starts with the word atom, that means this is an entry for an atom, then the atom number, then the atom type, like it's a nitrogen, carbon, and so on. The residue name, like serine, a chain, a PDB can have multiple chains, and residue ID, and then the coordinates. Okay, so there are like 3 coordinates, X, Y, Z. And then there is another factor called beta factor. We don't need to know that. What I want you to pay attention is the atom information and then the chain information. Those are the information we need. Sometime a PDB file. Yes. Yeah, anything with apt get, don't run. There's something about it. No, you keep this one. You keep this one. That will be easy to communicate. Yeah. It's in the bottom.
I'm not using
Not-
it. Etc. Please do not do any of those. All of those.
If you go down at the bottom of the PDB file, as you're scrolling down, you'll see your chain number change from A to B. That means like this PDB has 2 chains, and not necessarily we'll need both the chains, and we'll come to that later. Just wanted to show you. And then if we go down further down the one, here you see that entry called heteroatom, het atom. What it means is anything that's written as an atom as part of the biological molecule like protein and so on. Anything that's written with a heteroatom, that means like it has other like ligand, like small molecule, drug-like molecule, metals, and so on. And in a lot of the cases, we do not, or water, a lot of the cases, we do not need those atoms. So anytime you download a PDB file, before we take it to the drug sniffer, you need to clean out a lot of the PDB file and then Vish has already cleaned up a version of the PDB file in the exit directory that he will go through it. But just to give you an idea, a PDB file is basically an atom, indicates that it's an atom, what kind of atom, and the 3 coordinates, XYZ coordinates. Okay? So we have downloaded the 3 VRI PDB file. Now let's see if we, yeah. Sorry, hold on, I can't hear you. If you download it. Yeah, so question is like, if we clean it up, should we just keep the atom and the coordinates? Definitely, but sometimes you want to get rid of part of the atoms too. Like say if you want to only work with one chain, then you want to get rid of the chain B and so on. And a little bit more details will be coming out later. So let's look at the 3 VRI. If you open Chimera X, the daily build, and if you just type open, I mean, you can open from your local file, or you can fetch it again from the RSC, from the PDB, because I had it open before. So, or you can file, open, and navigate from your 3 VRI. Or you can just type 3 VRI. Either is fine. So this is our protein. And if you look here, let's see if I can zoom it. If you look here, what you are looking at, the ribbon structure is the protein. And in reality, the protein does not look like that. You know, your protein looks like a blob. But however, to be able to see the pattern, we represent the protein either as this curly alpha helix or beta sheet and so on. And inside this alpha helix and beta sheet, you can see a ligand. And this region is like a pocket-like region where the ligand is sitting down there. In this tutorial, what we will be doing is we will be removing this ligand. And there is an additional chain here. We'll be removing this additional chain, chain C. We'll be removing part of the chain B, which is on this part. Okay. And we will be only working with chain A. So now let's see. If we click on, well, okay. In case you do not have a structure of your protein, and we'll go through it in coming weeks, you can actually use structure prediction and AlphaFold from Chimera X. And we'll go through it. But in our case, we already have the structure. And Vish will show you quickly how to clean it up. So once we have the structure, let's say 3 VRI, and you can see there are 3 chains A, B, C. A is this part, B is the beta sheet part, and then C is, C is, there is a little bit of C here. So once we clean up, and we'll clean up, we'll keep only A, and we'll remove the ligand. The next thing is like, how do we predict a pocket? Now, in this case, we already know the pocket. We don't have to predict a pocket. However, typically, if you have an unknown protein where you do not know the pocket, we use multiple different protein prediction, pocket prediction software, okay? And I'm going to just show 2 of them. We are not going to run them today. So FTMap is a free server. You have to get an account, free account. Once you get an account, you can upload your protein. How FTMap works is like, it's going to take a bunch of fragments that Vish was telling, like how you build the Legos the Legos of, for building de novo design. It takes a bunch of those and try to dock it. Wherever there is a bunch of those fragments dock, it identifies as a pocket. So it's a different philosophy. It takes the small fragments and try to dock it. So when you do FT map, you'll get one kind of definition of pocket. Another one we use is a totally different definition of a philosophy. It's called Pocasa. Again, what Pocasa does is instead is like, typically that's how a protein looks like. What Pocasa does is like it rolls a ball, goes around the protein surface, and wherever there is something like a cavity, it will identify that as a pocket. Now, these two are total different philosophy. The reason we take these because there is no right way of predicting a pocket yet. So we combine these two, we use our knowledge, we say like, okay, this can be a pocket, that can be a pocket. And then once we identify the pocket, then we start the drug sniffer. Now, I'm not going to go, because of the time, I'm not going to go into the details of it. However, anyone who are working with the drug sniffer, we need your help in protein, pocket prediction or cleaning up, will come and individually help you. So the pipeline, automated pipeline of the drug sniffer starts after you have identified a pocket. That needs a manual intervention. You find the center of the pocket, you define the size of the pocket, and from then on, the software starts doing their work. So I think Vish is taking a break. Oh, there it is. Okay, so while Vish is getting ready for the next part, do you have any question about this? We didn't go through it details just because it takes a lot of time, and we'll go through it whoever is running individually. Just to give you an idea, you have to identify the pocket using this kind of server. FT map typically takes a day. Pocasa can be returned answer within a matter of half an hour or so. So if no other question, we can wait for Vish to start next part. Logged into the
Yeah, I think that's what. Yeah. Right. So everyone fixed the Docker issue? Has everyone fixed the Docker issue? Okay. And so currently you have the protein. You have, which is 3VRI, which is your target protein. You also have an idea of where the pocket lies. So for keeping it simple, we are going to remove the ligand from its existing pocket. And later on, we're going to try and redock it. So we're going to try and see if the docking program is able to get the crystal structure orientation. And in doing so, is it able to give us a binding affinity that is close to the experimental value? Okay, so these two things we'll do a little later. So before we kind of go any further, there are a series of steps that you will have to follow. Now, in many of the softwares, you may see these steps kind of automated. So if you were to use something, does anyone use Schrodinger, Glide, for instance? So some of those programs can actually do these for you. So there's this protein preparation step and ligand preparation step, and they kind of hide all this in the background. All you have to do is point and click, and your job is pretty much done. But if you were to do it the hard way, or what I consider is fairly simpler, you would have to go through this process. So yesterday, you probably did a lot of SCP, right? SCP, SFTP, and so on. Now, that is basically for transferring data from one machine to the other. If you're basically just transferring on your own machine, you would simply use CP, which is copy, okay? So I've created a folder called /data/shared, okay? So if you just list the contents, which is ls/data/shared, you should be able to see the protein 3vri.pdb, which I've downloaded from the PDB, which is Protein Data Bank, okay? Is everybody able to see that file? You simply have to do ls/data/shared, okay? And the next step you're going to do is to copy that file. You go, okay. Okay, now you're going to copy that file into your working folder, which is /data/username, the username being whatever your username you have chosen. Okay, so you need to copy that into your folder. And for that, we basically are doing CP, the location, and dot. Dot simply implies it's in the current directory. Okay, has everybody copied the file? Okay. If you now were to do more is a simple command to look at the file without any editing or adding or any such thing. It's just kind of a quick look at your file. So you should be then able to see at the top things like remark and so on. Are you able to see all of that? Okay. Now, has anybody or did anybody go through grep yesterday? Grep in your Linux tutorials? Or yeah. Okay. Rose, you want to take over? Grep? The bottom.
Does this work? Yes. I'm not going to do a thorough review of grep, but grep is a program that you can run. The example that's up there on the screen is just I don't have the laser pointer, just the first part before the pipe is a statement that says, look for the letters ATOM, atom, on a line in the file 3vri.pdb. And if a line contains that series of letters, print it to an output, otherwise don't. So it will filter for only those lines that contain the word atom. And that's what grep does, is it searches for a pattern and returns only those lines that match the pattern. The command that's on that screen then has a pipe character which says, okay, take the results of that and send it to some other program, which happens to be another instance of grep, which now searches for the lines that have the word remark. And because it's got a -v, it says, ignore the ones that have the word remark in them. Interestingly, one of those has quotes around the word atom and one of them doesn't have quotes around the word remark,
Won't matter.
you can ignore the quotes. That's the simplest tutorial I can give on grep. It's basically a pattern matching that either returns all the lines that do contain it, or if it's got a dash V, returns all the lines that don't contain that phrase.
Thank you. So, as Travis mentioned, the vertical line is what we call a pipe. It allows you to string commands together. So you take the output of one, feed it to the other, and so on. And this can be done as a chain. And that is the reason why you use a pipe. Now, we've basically extracted so in your PDB file, you have lines which start with atom, which is what we are interested in. We are also interested in a particular chain, which is chain A. Okay? So we want to extract all the lines containing the word atom and also the lines basically that contain the chain letter A. And to do that, we are basically going to use another Unix command called awk. And what it basically does is to say, if the fourth or the fifth column in the PDB file is the letter A, print it out. Is that clear? Okay. And the reason why I've had to do this is because PDB sometimes is kind of weirdly formatted, and there is no strict spacing requirements, or there is, but it's kind of weird. So you will then redirect the output to a file called 3vri_v1, which is basically for version 1. Has everyone followed that step? Anybody having problems getting to 3vri_v1.pdb?
So, because your line is
Oh,
so the copy paste will not work.
yeah.
You have to
Yeah. Okay. Now, because I was trying to create the document, one Okay. In the command that you're basically seeing in the grep, could you not put the backslash? The slash before the dollar, the backslash, the one that is leaning towards the left. Don't put that. Yeah. If you're basically on line 3 here, which is grep atom so on, please do not use the line leaning to the left, backslash, which is what we call a backslash. So which is preceding the dollar sign. It precedes the dollar sign. So if you don't do that, it'll work fine.
Okay, so you don't need the back.
Yeah. But I moved it.
Okay.
Yeah. So right. Has everybody managed to get through to 3VRI underscore v1.pdb? Do not use the backslash that precedes the dollar sign. And it should work fine. It's my mistake. Apologize. Yeah. Yeah, all of them. Please remove all the black slashes that precede the dollar sign. Okay. Has everyone got to 3VRI underscore v1.pdb? Okay. Now, if you were to basically just do more 3VRI underscore v1.pdb, you should be able to see only the atom records corresponding to chain A. Is that the case? If not, let me know. Is that okay? Okay. We then move on to the next step. Now, what happens in many PDB files, if you were to kind of just say more space 3VRI underscore v1.pdb, and if you go through the list, you will see in many cases there are some residues which have names like AASN and BASN and so on. And this typically is associated with the C alpha atoms of the residue. So you should be able to see that if you just type in more space 3VRI underscore v1.pdb. Are you able to see things like AMET, BMET, and so on? Yeah, so these are the cases where you have multiple instances of some of the residues. So what we need to do is, before we can proceed any further, we need to chuck those out. So either you can choose to remove B or the A ones. So you can either remove AMET or BMET. Now I've chosen to remove B. And because I have several such instances where I have BMET, BASN, and so on, I have put all of them in a single chain. Okay? So this command will allow you to do it in one shot. You can remove all the lines that basically have multiple instances of the residue using just this simple command. And the reason why we basically have this backslash and pipe is because grep generally works with just single matches. So for instance, in the previous case, you were doing grep atom. Now, if I said I want to basically also do het atoms, which is the ligands or the water molecules, I could simply say grep atom backslash pipe and het atom. which means it can do multiple matches in one shot. And that is what I'm doing here with this grep command. So has everyone got to 3vri_v2.pdb? Yes? Anybody not there yet? Please raise your hands. Okay. Anybody else? Okay, sweet. Right. Now, in some files, some PDB files, you will come across this word called aniso, okay? Which is basically all these anisotropic temperature factors. You don't need those in the file, but thankfully in your 3vri_pdb, you don't have those. So the command I've put in, which is sed, allows you to remove those if they are in the file. So since they are not there, you don't have to worry about it. So let's move to the next command, which is using OpenBabel. Has anyone heard of OpenBabel before? Okay. OpenBabel is basically a file format exchange software. Now, you have only come across PDB. There are several other file formats. For instance, there is something known as PQR, PDBQT. All of these you will be using very much in protein-protein docking, as well as in protein-ligand docking. And OpenBabel is a utility that allows you to convert one format to the other, simply because several different softwares are written using different formats. So if you follow the last command that you can see here, what you're doing is to convert the version 2 of the PDB file that you just created, and you're going to format it as something known as 3vri_rec.pdbqt. Amit, are we breaking for lunch? Now, in some cases, you would also be interested in adjusting the pH. Okay? So alongside that OpenBabel command, if you basically add last command you'll be doing before lunch. Yep. Just
All right. Okay.
Right. Now, I would like you to kind of just type in this command, open label, which is your version 2 of the PDB file, minus O PDBQT, and minus O. So it's basically converting the PDB to PDBQT format and saying that the output should be written in 3VRI underscore rec.pdbqt. The minus P is basically the pH. Now I've basically arbitrarily put 7.4. You can choose your pH. And XR. Yeah, for now just ignore that, okay? Okay, has everyone completed this command? Now open label might give you a warning or sorts. Ignore that. Don't worry about it. As long as it doesn't crash, we are not worried. Is that okay?
Warning. Does the
Yeah, that's okay. Just ignore for that. It'll probably print a warning like fail to caculize molecule. Just ignore that warning. Are you going through the VPN? Right. I think we can break for lunch here and then come back.
So, because we are running a little slow, come back at 1:30, 12 to 1:30. Let's back at 1:30.
Does anyone need any help with intermediate to advanced Linux? Something where we go over environmental variables and subshells, great, shells and subshells and subprocesses, and just, okay, great. Anyone else? Okay, great. We got, yeah, just going, well, it'll be mostly environmental and also bash scripting. All right.
Okay, we are a little tight on time. You know, while you are watching the monsoon, I'll make a quick announcement. So at the back of the room, there is a Excel spreadsheet printout where if you want to share what kind of experience you have, like if you have experience in molecular dynamics or RNA-seq, just mark it. The reason being is like other students then get to know which students to approach if they have questions and so on, okay? It's not, you don't have to do it now, but just go ahead and do it so the students get to know what kind of their expertise they have. Okay, and we will start the next part now.
I'm going to change the other tutorial a bit.
Okay. While Vish is getting ready, I'm not sure if we have announced the drug sniffer page. It's drugsniffer.org. Drugsniffer.org. There is a link to GitHub page there. If you want to install it later at your home institution or somewhere else, you can, clone from the GitHub or download from the GitHub and run it and modify it if you want to modify it and so on. And then some of the tutorials that Vish is going through today is also there, not all of them. That's also available there. And also later, we will have, during one of the lunch break, a little longer lunch break, within the next few days, we'll have a trip, if you want, to check the HPC Center of the National Biobank and also the biotech, the other hub. And there will be a sign-up sheet behind there. We haven't decided the date yet. It will be during one of the lunch break. Feel free to take the opportunity to see really how a HPC room looks like, how much hardware there are, and so on. And we'll announce that shortly. Okay, I'll wait for Vish. Oh, and then we hope to finish this workshop around 3. And after a short break, we will start a separate tutorial on machine learning, which will be the beginning of like a beginning machine learning for beginners, where you'll learn a little bit of machine learning and we'll predict the secondary structures, right? So, yeah, we'll predict the secondary structure of the protein using machine learning. That will be, hopefully you can start around 3. Oh, one more. Until Vish is getting ready, you are free to watch the monsoon again.
Right, everyone here? Those, okay, they are just, okay, so right now we are still in this protein preparation phase. So you've done the target identification, but there's a bit of preparation to be done before you can proceed with the next few stages. So I have uploaded a new version of the tutorial, which I would ask you to download first before we can go to the lecture materials. Yeah. So it's in the Slack channel, lecture materials. There's a new version of the tutorial. Ooh. Has everyone downloaded the new version? Yes? Okay, sweet. Look, this is slack.
Right.
Yeah, yeah. Oh, you got a Slack app. Okay. Yeah, yeah, it's the latest one. Then you know how to use the advanced stop share, advanced feature, and then just you want to do this. Left off where you had your 3VRI underscore V2 version. Okay. Now you will be converting this into a PDB Qt file, and you will be adding these two additional options, which is basically XR and -P. So the -P is to alter the pH, and XR is to kind of produce a slightly reduced size file, which OpenBabel will have to provide you with. If you do remove the XR option, it doesn't matter. It's just that the file size might increase significantly. Okay, so has everyone done that step? Have you reached? Okay, great. So you've now done the protein preparation for a docking step. You now also need to do the same for the ligand. So if you go back to your original 3VRI.pdb, now you will search for het atoms, which are the ligand atoms. Now it turns out that the water molecules are also called het atoms, so you would probably see them as HOH in the PDB files. Do you see them? If you look at your PDB file, 3VRI.pdb, if you just do more or basically look at the bottom or the tail of the bottom portion of the PDB file, you should see something like het atoms alongside with HOH sometimes, or the ligand name. Is everybody able to see something like that? Okay. Now, we're going to do the same. We're going to convert the PDB to PDB-QT format using OpenBabel. But before we do that, we need to extract the lines that contain het atom. And just as you did before, we're going to use the grep command. We're going to search for lines that contain het atom. And then we want to exclude all the water molecules, HOH, okay? And also, this is, okay, yeah. Where is that arrow coming from? Is it frozen or no? Okay. Okay, we don't have haven't copied the files here, so yeah, I haven't copied the files into your directory. You'll have to, yeah. Yeah. No, I mean it's like you just need to copy whatever I've done. That's why I said ignore that. Now, if you just go back to the tutorial, you should be able to follow. Okay, so okay, So if what I'm trying to do here is to extract all the het atoms, exclude the water molecules, and also remove the sulfate ion. You can then store all the output or redirect the output to the file 3vri_lig, lig for ligand. And once you've got this file, proceed to the next step of converting it into a PDB-QT file for the ligand. So you have a PDB-QT file for the receptor. You also have the same for the ligand. Okay? Right. Now, some of you will face an issue with metal atoms if they are present in the protein structure. Now, open label doesn't like metal atoms, so it doesn't handle them very well. It usually crashes. So if you have metal atoms in your PDB file, you'll have to take them out, copy paste it, or cut paste it into a different file, do the steps that you did previously, and then put it back in. And for that, you will need a proper text editor. So please do not use Word. It's going to destroy the formatting of the PDB. Okay? Yes, I think this one. So has everyone completed the step of creating the ligand? So you should have in your folder a PDB-QT file for the receptor named 3vri_rec.pdb and a corresponding file for the ligand. Okay? So this kind of concludes your protein preparation step. Now, this is typically automated in some of the more sophisticated softwares. I'm taking you through this step, and if you were to run the original drug sniffer flow, you wouldn't have to do all these steps. It automatically takes care of all this. All you need to then provide is the PDB file, and you're done. Okay? Now, the next stage is to identify the pockets or the potential binding pockets in your PDB file on your protein target. Now, as Amit mentioned, you can use online tools like FTMap, which I would recommend. On the off chance that you do not want to do so, you could use something known as fpocket. Now, fpocket is not installed on the server. It's a separate piece of software, but it does require you to compile it. So if you're not familiar with compilation, probably best to ask a system admin to do that for you. Now, I have only put a simple command for fpocket for you to play around with if you do have access to fpocket. If you do not, don't bother. For the example that we have, which is 3vri, we do know the binding pocket simply because we could just remove the ligand, and there you have the binding pocket, which is essentially what you have in your 3vri_rec. All you need to now know is what is the center of that pocket. Okay? So center of that pocket can be simply done by taking, for instance, the center of the ligand. So if you average the coordinates, you should get the center of the ligand. So moving on. So in the drug sniffer pipeline, as I mentioned, there are 7 stages. The first 2 of which is done externally, which is what you have done so far. The third stage is the de novo step. Now, this is the step where you try and create a molecule that is likely to bind to the pocket that you have left vacant. Now, we have a Docker routine that does it for you, but I would recommend that you do not run it now for the simple reason that it takes a long time. If you do that now, you will have to kind of wait for a very good length of time, by which time you would have concluded the rest of the lecture. So I would suggest you wait for this de novo step to be completed at a later stage. Now, to kind of make matters easier, I have created, or I have previously run the de novo step. And if you can access, just go to the console, ls. If you type in your console ls/usr as in user /local/tools, / drug sniffer, drug-sniffer, / examples. Just ls, enter. Yeah. Is everybody able to see the text? Okay. So if you were to just type in the ls command, you should be able to see a file called 3vri_seeds.smi. Are you able to see that? Yeah. So those are the output from the de novo step. Yeah. No, you have to. It's on the. You just go to the previous. Whole thing. Oh, no, the more. No. Right. So if you can all see the file here, this is the output from the. Okay, you want to go just Q and show the command again. Just Q. No, you're in more. You won't be able to see the screen. Yeah. You'll have to get out. Is everybody able to see that now? Just press enter. Yeah, that's all. Right. Can everybody see the file? Was everybody able to access the file? Yes? Yep. So in this file, you basically have a series of molecules which are identified by these smile strings. Okay, so as I mentioned, hash implies a triple bond. A bracket implies a branching. Equals implies a double bond. You don't have to identify single bonds in smiles. So this is simple plain ASCII text. And towards the right, you have the name of the molecule, which is a fairly long name, but it basically means this is generation 6. So we have run the de novo step for almost 25 generations. And this is the 6th generation in which a molecule was found to be quite good. Quite good means it had an optimal binding affinity as predicted by the docking program. And this basically specifies that this is a crossover between two molecules. So it's a bit like exchanging genetic material. And if you go further down, so you will basically see that molecules from different generations are effectively being crossed to create new structures. And this process is repeated iteratively over several different generations before you kind of see either a plateau or something which is optimal.
In the first few molecules, I see the same structure, C triple bond, CC, double bond NO. So why there are 3, even though the molecule is the same?
Yeah, because let me also point out that the autogrow doesn't actually do a proper check for unique structures. It only does it towards the end of the program, but that's usually also not done. We have to do it. It's one of the reasons why we would like to replace this program. But you do get a lot of structures which are duplicated. So you would have to do a post-processing step to extract only the unique structures that you want to work with. Does that answer? Okay. Now, if you go down further, towards the end. Yeah. Must be a mutation somewhere. Is there a mutation in this? From looking for this. Yes, just grep mute. This is grep mute. Yeah, grep MUT. Oh, it might be M capital. M, yeah. Yeah. Oh, yeah, there is a mutant. Yeah, no, just do. That's okay. Enter. Yeah. No, but okay, you might also see something like mutant. So this mutant basically means that the structure was originally mutated and then crossed over with another structure. And if you actually go through the file, you will also see some structures which are labeled mutated. And that would mean the structure had a single mutation of sorts. And a mutation typically implies that the fragment was replaced with something different. If it gives you the same fragment, which means it's a duplicate. Or if it gives you the same molecule, it's a duplicate, of course. Yeah. There must be another mutant somewhere. But anyway, it's okay. Yeah. So this is the step that you will be doing as part of the whole next flow chain. You don't need to do this right now. Okay. So we'll move on to this next step, which is basically step number 4. So we have kind of skipped step number 3, which is the de novo part for now. And we are moving to similarity search. So if you remember similarity search, what we want to do is to expand the library of structures that we have created by trying and identifying structures that are similar to the ones that we have here, with the expectation that if these have good binding affinity, the similar structures are also likely to have a good binding affinity. So this step you will have to perform on your, yep. By the uncertainty clarity. So she wants, so she wants to know how, having performed the similarity search, how would you quantify the uncertainty associated with the similarity step? If there is any uncertainty in your similarity. Sorry, could you just speak in the mic?
You said that you're going to use some threshold to choose like 10 similar structures or something. So I don't understand where that threshold comes from. And also, how would you know, like, shouldn't there be some false discovery rate sort of associated with something like this?
Right, come to that. Sorry. Now, I'll answer her question while you are actually copy pasting the next step. So if you, you need to go down. Yeah. So, yeah. So this is where you need to be. Oh, sorry. This is where you need to be now in the tutorial. So what we are doing first is to copy a small database that we are going to search against. And the query structures will be provided by the de novo ligands that you just saw. Okay, so each molecule in this file is going to be treated as a query. And we are going to use the small database that we have created as a lookup table to see if there are structures similar to the ones that are output by the de novo step. Now, her question was, how do we know what is a similar structure and what threshold do we apply? Now, as I mentioned earlier, that we do use a similarity metric called a Tanimoto fingerprint or Tanimoto similarity metric. And the Tanimoto similarity metric simply measures how many bits are on in both molecules. Now, the problem here is that the value goes from 0 to 1, where 0, as I mentioned, implies no similarity, with 1 implies perfect similarity. Now, you would expect that a highly similar molecule is also likely to have a similar activity. In that case, you could decide I might arbitrarily choose a threshold of 0.9 or 0.95 or 0.99. The problem is there's no easy method to decide this is the threshold I'm going to apply. And therein comes the concept of uncertainty, because you're not sure where do I put the threshold. So it also happens, or there's also the problem that you're not entirely sure that if you put a threshold too low, you're likely to have too many structures in your output. If you put a threshold too high, you may not even recover structures that are similar at that threshold. So it's a bit of a trial and error method. Our experience has been that in some of the examples that we have tried, we have had to lower the threshold to as low as 0.3. But it is not the optimal value. The optimal value is unfortunately difficult to determine ASAP. So I would suggest let's try with a simple threshold of 0.5 and see how many structures come out. If you think at 0.5 you get too many, you can increase the threshold to 0.7. Or if you think there are too few, you can lower the threshold to 0.3 or less. Just don't put 0. Yeah. So has everyone managed to do the first step of copying the small database? Okay. Now, everyone recalls why we are doing CP minus R? Yes, it's a folder, so you have to recursively copy everything. The next command is, again, you're going to copy the seed database, which has got all the de novo ligands. So please do that as well. The dot implies you're going to copy it into your current directory. Okay, has everyone done this step? Yes? Okay. Right, now you've already seen the contents of the file, so I'll skip this one. Now, could you try and copy paste this command? Just don't run it yet. Just copy paste this command and paste it on your console. Yeah, now in this command, there is something known as a username. I would suggest you use the username that you have been provided with, or the one that you've chosen. So if it is in /data, and if your username is Daniel, so I would suggest /data/Daniel/output. Is that okay? Nope. Yeah, so if your username, instead of this capital username, put the name that you have created for the folder, whatever your folder name is, where you have created, say, with your name, Daniel, or here you have all the students here. Yeah, so you have, yeah. Yes, just don't copy paste it into RF's or somebody else's account. Yep. Yeah. Yeah. Oh, if you copy the. Mhm. Mhm. Why?
Maybe I did not run the last
No,
command.
you don't need to. You should be able to just copy this. Oops. Hmm. You just tab. Hmm. Yeah, and then dot. Yeah, so it's there. Now, if you do more, in.
I just didn't get.
No, because I had already shown you the file. So if you want to see the file, you can do this.
No, this is talking
Okay.
around.
So this, all you need to do is copy the whole thing, except change the username, just this username, to the one you have. Yeah, just run one. Therefore, when you paste, it might want to copy it line by line. Otherwise, it will also copy the entire. Okay. Yeah. Do it one line at a time.
If you are copy pasting this line, there is a small typo here. So it is written as small underscore db. It should be small hyphen db, the file that we copied here. So in this one, just change it to small hyphen db.
Don't worry, please. Yeah.
And
And
I didn't get the
yes.
older one.
So what's your username? What username are you using? Do you have a folder name?
Yes.
Yeah, so change that username to your folder name. So if you've created something like, what's your name, sorry? Athia. So you must have created a folder called Athia. That's the one. Yeah. And also change the small underscore to small hyphen. Small underscore, I made a mistake there. So you have the small db, small underscore db. So just make it small. So put small dash IB, small, no, instead of underscore. No.
Here.
Yeah, instead of the underscore, remove that underscore, put a minus, and then enter. It should be, hopefully, good. Yeah, it's run. I'll come to that. Is everyone's internet working fine? Anybody got internet problems? Two, okay. Okay, thanks, man. Thanks for that. Okay. Has everyone replaced the username with the folder names or your whatever name you've chosen? Okay. So now you should be able to press, and you've also made the change of small underscore to small minus or small hyphen db. If you've done that, you can happily press enter. You did. And you should now be able to see if you list the contents of your file, of your folder, if you just do ls, you should see a directory called output. Okay. And if you were to look at any of the files inside that output directory, oh, what I would suggest is don't copy paste the full copy line by line. Okay. So if you go back to your PDF, copy one line at a time. After minus E, Because the thing is, it's like it's one single command, but first have to basically write it to overrun the PDF. Okay, so copy it one line at a time, put a space, and then paste. Try that. Okay. Yep. Yeah.
Are they supposed to create it, or are they supposed
So
to?
receptor or PDB? Which one?
So, can you go to these?
Oh, you don't. No. Thing is, this is a. I've just given you an example. This is when you have metal atoms in your protein. Then you open the receptor, whatever protein.pdb or receptor.pdb is. Then you open that in a text editor, take out metal atom, paste it in a different file, do this process of converting it into PDB, PT, and then add it back in. Otherwise, OpenWeb will crash.
So also, how do I download this? If I jump to this part, like
Yeah, because we haven't installed. This is basically just for your reference. If you do not have a binding site recognition program, you can try and use Pocket, but the installations, etc., will be left to you.
Okay.
You can't follow
So
that.
like we are directly jumping to the stage 3 right now.
Okay.
Thank you.
So right, has everyone run the command? Yes. Yeah, just 1 second. Yep. Are you in? Oh, no. You forgot the username? You didn't put the username?
The 20.
Yeah, so you basically put, no, you would have created a folder with your name, right?
Yeah.
Is that is your,
Okay.
that is your name. Okay, so you basically put /data, whatever is your, sorry, what's your name? Okay, so you basically use Maliha, right? So it's /data/Maliha/output.
It's actually going somewhere. It's actually going, they're creating because there's a PWD flag.
Oh yeah, so that's
So it's creating under their current file, there's
another
username
business name.
and there's, okay. Creating
Somewhere else, yeah. Okay, that.
hold on. Creating, but there,
Yeah.
under there is, they created a username.
Yeah. So it's okay. It's not in /data user there.
It's creating whatever, because you have the PWD.
Yeah. Okay. No. That shouldn't be the case.
Let's see. Who has these one?
Daniel.
Okay, so let's see. Let's see if everybody is out.
Yeah. Where was the output folder created for you on your side?
It does create an extra folder. It does
Okay.
Daniel/Daniel/ exactly.
Okay.
It's under the username.
Oh, okay.
If I did just slash, I got it.
Yes, output. Yeah. Yeah. Okay. Doesn't matter. It's still there. So has everyone finished this step? Yes? Okay. So, great. So you should be able to find the output in whichever is your present working directory. You should be able to see another folder hierarchy which says /data. Sorry.
Yeah, I think that the files are being created wherever you ran it from. They created another of your username and then /output. That's where the files were created. So see if all of you have the output directory. If all of you have the output directory, then we are good to go.
You have a directory called output.
Yeah. Okay. All of
That is
them.
the case, that's good. Okay. So if you are able to look at the contents of the output directory, that'd be great. So if you are able to ls and see what is there, that'd be nice. Can you all do an ls?
But I don't think they contain.
No. Just is what is search data? Yeah. So if you do ls of your current folder, just to control C, yeah, ls of your current folder. So it's basically inside.
Yeah.
Okay. Yeah, there it is. ls.
But if
Should be there. That's funny. Okay, just look at flash.
another folder, yeah. Folder. No, my folder is just empty. Oh, empty here. Yeah.
Okay. Do you have a slash data here somewhere?
Slash data. Yes. No.
This thing.
Oh.
Did you download Ruxniffer or?
Yeah, I downloaded that.
Okay. Everyone able to run the command and see an output folder? No? Yeah.
Yeah.
Um,
Can I copy? Back. Oh, I don't know.
Travis? Yep. He's a bit more of an expert in how this was set up. Great. I'll have to ask him to knows a bit more about what happened here. I think you can solve that problem. Like,
I was thinking that they originally did it in different data and already a little bit full, maybe.
that's what the thing is. It works for them. Works for all of them. Travis,
Files aren't being written to the right place?
this shouldn't be happening.
Oh, what's
Yeah,
happening?
I'm getting like Python. Like I'm getting actually.
Why am I getting?
Yeah, it's like referencing other programs.
Happens inside of Docker. Error is first. You put an underscore.
Oh,
or
did you
are
put a
supposed to
dot
have
there?
dash?
Oh,
It's supposed to be a dash, right?
yeah, it's supposed to be dash. I think that's okay.
No,
It's
no,
a
but
small
it's got
minus
an under,
db.
isn't that supposed to be a dash there?
No, that's the.
It's
where
by file,
no,
it's
no,
all
that's fine.
Oh,
It's
small
saying-
db.
Yeah.
Okay. Oh, I see. Okay. I make it bigger. Oh, you know what I should do?
Because we shouldn't be getting Python errors. I want to. Oh. You weren't among the ones. Sorry, you weren't among the ones who uninstalled or
I
installed Docker,
really
right?
do not believe I had installed Docker.
Thank you.
Yeah.
Second call. Yeah. So, yeah.
0.88. Okay.
Then followed by X. So there is two values. Only answer.
Yeah. And then 0.39, that is how bad?
All these values suggest.
Oh, okay. And what's
Second number is ability.
okay. Okay. And can I run just any of them, like multiple of them, like any? Okay. Yeah. Thank you very much.
Oh, there we go. Okay. So what happens is you don't have an environment variable called seed ligands.
Yeah, there we go.
So then it's gonna. He had an S, an extra S.
That's the issue.
He had
Just that small.
I have an underscore instead of hyphen.
As a debugger.
Okay. So is everyone on the same page regarding this step? Anyone else who's missing out? Nope. Were you able to look at the contents of the output folder, and you should see a list of or a set of SMI files, .smi files. So what basically it says is that using the seed ligands, that is your de novo ligands, which is the underscore seeds.smi, you use the Tanimoto cutoff of 0.5. You said, I want all the molecules in the database that have a similarity of 0.5 or above. Now remember, the Tanimoto value goes from 0 and 1. 0 implying no similarity, and 1 implying it is perfect similarity. Okay? So at 0.5, you would be getting some 20 odd structures. I think 27. Are there 27 27 SMI files on 20? Oh yeah, sweet, sweet. Yeah. Is he positioned here? He's perfect. So Daniel is sharing his screen, and you should be able to see what he gets, and that's pretty much what you should be getting as well. Daniel? You have the output directory. Yeah, so you should see 29 files, yeah. So around 29 files in that directory, and you can actually go and see each file separately and find out what kind of structure has been retrieved. Okay, so this is your Tanimoto cutoff to identify the closest or the nearest neighbors. You can increase the value. There's a high likelihood you're going to get less than the 29 that you see. If you reduce the threshold, you should get way more. Okay? So you can experiment with this a little later. Can we go on to the next step? Yes? Oh, here, okay. Oh, that's a good idea, thank you. I'll just go into the next one. So we are now proceeding to stage 5. And if you remember, we have now prepared our protein, we have prepared our ligand, we have found the pocket, we have done the de novo design step. We've also done a seed or a similarity match to basically expand the data set that we have. And now the question is, are these as good as the de novo ligands, or are they better? So what you're going to now do is a docking step. Okay, so you are actually going to try and dock the ligand into the protein pocket. and what you should get is a binding affinity. And then we decide what can be done. Now, because there is this step is also can be time intensive, I have given you a simpler example where we are just going to take abacavir, the original ligand that was bound to this protein, and redock it. Okay? So what you see here, this smile string is basically the molecular representation of abacavir. Okay? Now, you don't have any 3D information as of now. What you have is just this ASCII string. And what I'll ask you to do is to echo. Echo is simply, as its name suggests, it's going to just print the same thing, which is double quoted. Whatever is within the quotes is just going to be printed. And we are just going to push that into a file called abacavir.smi, which is a smiles file. Has everyone managed to go through that? Okay. Now, you have already prepared the receptor, if you remember in the previous step. If you recall, you should have in your folder a file called 3vri_rec.pdbqt. Yep. So we can skip this step, but you still have to prepare it for the ligand. Okay. Now you had done the same step using a PDB format where the coordinates or the three-dimensional coordinates are known. But as of now, let's assume that we do not have access to that data. So the first step is to convert this two-dimensional structure into a three-dimensional form. And to do that, you're going to use OpenBabel again. So your command would be basically the input, the smiles file. The output is the .stf file. I'll show you a little later once you've gone through this command. And what it is asking OpenBabel to do is to generate three-dimensional coordinates for this molecule. And the minus H indicates add the hydrogens as well. It does add it by default, but you can always add the minus H option in OpenBabel. So let me know if you have managed to complete this step. Done with it? Yeah, so as of now, you've come across .smi files, .pdb files, .pdbqt files. This is another molecular storage format called SDF, or standard data format. And if you just did a more abacavir.sdf, you will see the contents showing the three-dimensional coordinates as an XYZ coordinates, indicating also the atom type. And you'll also see in the fourth column whether it's a carbon, nitrogen, oxygen, or hydrogen. Hydrogens will typically be at the bottom. Okay, so this is your three-dimensional, and this is just one conformation of the structure. There could be potentially multiple conformations, but for now, we will stick to just a single conformation. Right, so next step is to convert this STF format into the PDBQT format, which is exactly what you did with the PDB format, except that now the input is a .stf file. Yeah. No, you don't need to go back. Oh, this one. Amit, how can we make the size on this side bigger? The idea? Yeah.
Yeah, I don't do this.
Okay, Amit, sorry, Daniel, could you just run the previous two? Just the Was it the smiles to STF part? If you just show her the command, I think that should. Oh, it doesn't fit into the line. Are you able to see this now? Yep. Hmm?
pH is minus P is for the pH 7.4. Can you please explain why you should mention the pH?
Okay. You can, of course, set the pH. Normally, it's, I think, 7.1 is the default setting. You can decide whether the pH should be changed according to the interaction that you are going to assume between the ligand and protein. So if you want a higher pH, you can do so. But remember that the charges will be different. Okay? So the charge calculations will be significantly affected if you change the pH. So the PDB-QT format, if you have, I'll take you through that a little later. So once you complete this step, please let me know. Has everyone finished this one? Right. Are you able to finish? I think just. Anyone else have a problem with this step? Yep.
We're trying
Charges. Charges. For now, we charges. If docking program does decide to use the data. There's an additional step coming up. So if you don't have any idea of what pH to use, don't bother putting the minus P option. Okay, so there's a default, I think 7.1, which OpenLabel has, and that will take care of it. Right. Everyone on the same page as of now? Okay. Next. Pretty good. PDF. Now, you're going to be using Autodock Vina to perform the docking. So you have the receptor.pdbqt, and you also have the ligand.pdbqt. All you now need to specify is, where is my pocket? And typically, we do this by specifying the center of the pocket. Okay? Now, if you remember in our previous step, we just simply extracted the ligand in its bound form. And we haven't changed or perturbed anything in terms of the coordinates. So if you take an average of those values, you should pretty much get the center of the binding pocket. Okay? The reason why we want the center of the binding pocket is that for Autodock V0 to work, we need to provide a search space. So it needs to know where to start. So if we say this is the center, we need to also tell it in all the X, Y, and Z directions, how much do I move? Okay? So by specifying 3 parameters, size X, size Y, and size Z, you're specifying essentially the dimensions of a 3-dimensional polygon. And to do that, so what you're doing here is, as I said, size X, size Y, and size Z. Now I've created a cube here of 10 angstroms, and I've told Autodock Vina to search for the position, optimal position for docking in this particular zone. And remember, the center of the binding pocket is being specified using minus center X, center Y, and center Z. Is this clear? Now, some of the other options that you will be coming across is, just a second. Some of the other options you will be basically coming across is num modes. Now, Autodoc Vina is going to give you several different alternatives because there are multiple orientations for the same ligand. It can be docked this way, it can be docked that way. So for every ligand, it will give you a default of 9 different orientations. You can change that value if you think 3 is enough. Okay? The next one is the seed. Now, this is it has a random starting point. So if you want to get the same results every time, it's best to provide a seed value, which means every time you run it, you're always going to come back to the same answer. If you change the seed, there is a slight chance it will change. The other option, which you're going to be using, is exhaustiveness. Now remember, we have a 10 by 10 by 10 space to search. So what should be the grid size that you need to, what is the grid refinement that you need to put in to explore the space? Do you want to go ask the program to go 1 angstrom at a time, 0.5 angstrom at a time, and so on? So if you increase the exhaustiveness, the runs are going to get slower. Your computational power is going to be used up. So you can decide whether you want a quick and dirty answer or a slow and equally dirty answer. So any questions on this one? If not, you can jump in. Remember also that Autodoc Vina is parallelized. So you can actually run it with multiple CPUs. For now, we are basically just going to be using one CPU. And the output will be written to a file called doc_abelsevir.log. And you should see something like what Daniel is showing right now. Is everyone getting that? The answers should match ideally. Okay, so yeah, that's what I was about to. We'll go back. Good. So the initial part of Autodoc just simply says what are the parameters you supplied, exhaustiveness, the XYZ coordinates, and so on. And if you remember, I said 9 orientations to be preserved. And you should see 9 different lines, each with a different score. And this is the binding affinity predicted by the docking program Autodoc Vina. We'll come to the scoring function a little later. And you can see it is being sorted from lowest to the highest. And because this is the reference, or this is the best orientation that was identified, a root mean square deviation is calculated for all the other orientations with respect to the reference. So for your interest, you should be focused on this value. So if you want to keep the top 3 orientations or the top 9 orientations, that choice is left to you. Currently, this is the docking affinity, or the binding affinity as predicted by Autodoc Vina. If you were to go back to PDB, search for 3VRI, and if you go down further, you should see a binding affinity, which is experimental. There should be a significant difference in the values, ideally. If not, just let me know. So you should be able to go to the PDB, search for 3VRI, and if you go scroll down the page, you should see a binding affinity value for 3VRI with abelsevir. Yeah, don't worry.
Just don't search for experimental.
Finding DB data for this right now, but there is, I know for sure somewhere. But in any case, I can tell you that the predicted value as identified by the docking program Autodock Vina and the value that is and the value you will probably see later on are quite different. Okay. So has everyone completed this step?
I think there's an error in in this open Babel command. The command itself in the documentation says to run with this _rec receiver, but the file is actually that.
No, it is _rec. You should have a REC.
Tried it.
Or was
and then
there?
I got an error.
No, that's because you didn't create the one. Because that.
Oh, what's the command?
If you go, that was a protein preparation.
It's hard to know. Got to pull down and go up.
So this is the place where you're basically creating VRI and lig. Right. Yeah. Oh, did I not? That?
I mean, how
Okay.
for
So you could use VRI. So I should have.
yeah, but again.
Yeah.
No. Just enter that for V2 here,
Oh,
but not PDR
This one?
PDB, right?
That'll be the whole PDB.
so
Yeah. It should be a 3 VRI.
Okay. Enter? Yeah, there you go. Right. Has everyone finished this step? Yes? Okay. So in the stage-wise setup, we have completed up to stage 5, which is to identify or having found the similar ligands, we have performed a docking step to ascertain whether the binding affinity for the similar ligands is going to be good or not. Now, when you do this, you would probably be doing the whole pipeline. So as of now, I've just given you a demonstration of what actually goes on inside the pipeline. And this has to be done for every molecule that you have found in the search. So if you had 27 molecules, you would be doing, or 29 molecules from your similarity search, you would be doing 29 such docking steps. And if you had a much larger database, as Amit showed you, we could end up having 1 million structures and you'd have to do 1 million dockings. Okay? Now, if you did this on a single CPU, it could take forever. You can parallelize it, and it will reduce it significantly. But if you all started, I have no idea what's going to happen to the server. Okay? So let's move on to the next one, which is binding affinity prediction. This is where I hand you over to Daniel, who has been the guy to do all of this.
Okay. So we have the scores from Vina. We have the docking scores. And we need to convert those into something that hopefully is closer to the actual experimental binding affinity. And so to do that, we're just going to run we're going to run all of our docking values through a deep learning model. And that will just output a predicted binding affinity. And the predicted binding affinity isn't actually a binding affinity. It's more of a probability in the range of 0 to 1, where 1 means that the model thinks the ligand will bind with the protein, and 0 means it thinks it won't. And to do this, we just have to run this command.
Get I underscore X. Great. So in the command, you have the thing called VRI underscore REC. So you can actually replace it with underscore V2 as well. Knowledge show is what Amit was describing. It's called DFire.
For physics-based core, you calculate positive, negative charge and Coulomb force. In knowledge-based potential, what you do, you go through a database, let's say PDV database or PDV ligand, and you identify which atoms are close to each other versus far to each other in the database, and how often they are close to each other. And if they're close to each other very often, you give them a higher weight. If they're not that often, you give them a lower weight. But that's another way of calculating binding affinity. The philosophy behind it is, if in the database 2 atoms are always close to each other, or 2 residues are always close to each other, they must have an attraction. That's why they're coming again and again in database. So instead of calculating the physics terms, you just calculate the statistics term. How many times 2 of them are close? How many times 2 of them are far away? And you create a statistical potential. The difference is, you hope if your database is vast enough that you can capture the entropic term as well, but that's not always true. But at least it's yes, it's the experimental data. Let's say PDB has a lot of structures. You can generate the potential from there. There are some estimate, like it is easy to count how many which atoms are close to each other. What is difficult to estimate is like, what is the expected number? Like if I see, let's say in PDB, lysine next to arginine 1,000 times, that's easy to calculate. But what is difficult is like, what is the expected number? And different statistical model differs by calculating the expected number. They have some different gas phase models and other models. They say, we expect it to be 90, we expect it to be 100, and so on. So the expected, how much is the expected in the nature, that part varies. But how many are in the nature currently in the database, that's easy to calculate. It will differ what? Hopefully not. The reason is like you are trying to capture the interaction between two atoms and so on. So hopefully, you want to put everything together. It's actually two directory above. I can help them.
Okay. Right. Has everyone completed this step? Okay. So what you should see is a .score file in your directories, which is ligand.score. And if you see the contents of the file, you basically have the SMILE string for abicavir, and it's basically the 9th orientation. Yeah, so you had 9 poses, and Daniel's program, which is doc to bind, is it? Yeah, doc to bind, predicts that the 9th orientation is the best one, and that it has a probability value of around 0.7. Ideally, higher the better, so that if you had several different ligands, you could rank them according to the probability values. Okay, so has everyone completed this step? Yeah, so you've got the contents of ligand.score. You know what it means, okay? All right, so moving on. This is the final step. Now, how many of you are familiar with the term admit? Yes, so. Oh yeah, I did, sorry. Right, so if you recall, admit had several different parts, which is absorption, metabolism, and so on. So what I've done is to create a program which offers you 58 different models, and you should be able to see all of those 58 listed models as you can see in the text. So there's a lot of models that are associated with toxicity, and as I mentioned earlier, that you will find several different forms of toxicity. There is muscle level toxicity, there is liver toxicity, and so on, cytotoxicity. So there are several different kinds of toxicities, all of which are data derived from experiment. And the ADMET models can be divided into 2 kinds. First, where it basically predicts whether something is going to harm you or not. You'll typically see in the output a yes or no, or negative or positive, something along those lines, or high, and so on. And in addition, if you want to decide which of these admit properties is applicable, so there are 58. Now, it doesn't mean that you can't run all 58, but you have to be selective about which properties actually apply to the problem at hand. So as I mentioned earlier, if your drug does not need to cross the BBB, the blood-brain barrier, you can use that model. Or if you do not care about other aspects, do not include those models. So a simple option here, as I've mentioned, is to use the options 1, 2, 3, 4, 5. So if you want to write 58 properties, if you want to output all 58 models, you'll have to specify 1, 2, 3, 4, 5 till 58. So if you want to do that, be my guest. So what we're going to do is to predict the ADMET properties, at least 5 of them, for abicavir. Now, ideally, toxicity should be considered in the way that the drug binds to the pocket, but many a time we do not have enough information. So these models are purely based on the molecule alone, that is based purely on the ligand alone. They have no idea what the receptor looks like. Okay, so they are completely receptor blind. So be aware of the fact that some of these, or many of these ADMET models can or will certainly provide a prediction, but how much trust you impose on them or in them is left to you. And in any case, the ADMET is going to be used as a filter So if you think there are properties that you do not want to be violated, so for instance, if you said liver toxicity is a strict no-no, you can decide to drop that compound and move on to something which is predicted to be valuable. So the same principle as before, just copy, paste the commands, and you should be good to go. Yeah, which one? The system is booted. Oh, you're still getting an output, right? Oh, it's done. It's done. Don't worry. So the way currently Nextflow is configured is that it requires you to run the whole pipeline. And because we cannot run the whole pipeline immediately, I'm doing it one example at a time. So you can only run one example at a time using this scheme. If you had several different structures to process, I would suggest you use the Nextflow pipeline. We'll come to that in the next 5 or 10 minutes. So try and complete this step, and I will explain the output. Any problems running this step? No? Has everyone seen a file called admit.txt in your output folder, in your output? You should see, if it's run properly, you should see a file called admit.txt in your folder. No, not underscore, just admit.txt. Yeah, good. Yeah. Mm-hmm. Oh, that is in the previous step, the protein preparation step. Actually. Oh, we should actually move directory. Because it's ideally we start working in data/data. Sir? Okay, if you run the command, you should see a file called admit.txt. Yes? So if you were to just if you were to look at the file, you will see plenty of columns. Some of it says negative, some of it says high, and so on. So for each of the properties that you have predicted, which is top 1 to 5, assuming you've done that, you will see a prediction. So the first one corresponds to anti-commensal effect. The second one, if you go back to the PDF, PDF. Oh, you can. Yeah, so the first 5 properties that you've tried to predict using the admit system are the blood-brain barrier penetration, oral bioavailability, which is an absorption property, and then mutagenicity, which is toxicity, and metabolic stability. Or, yeah, it's, okay, the output file is admit.txt. You should see a file called admit.txt in your folders. Okay. Now, if you look at just the first 4 columns, the first column would be ideally the name of the molecule. The second column would be something like negative or positive, depending on what you got in your predictions. So it basically says that it is negative for anti-commensal effect. You can look it up as to what it means. And then the second and the third and fourth columns are 2 probability values. I'll first focus on the first one, which is first value, if you can show the, yeah. So this 0.90 simply says that we have a high confidence that there is only one prediction possible. It can be only negative. The other one also says what is the confidence we have in this prediction, which is around 0.85. Ideally, you would want to reject the cases where the uncertainty is less than 0.5. So if you have a probability which says I'm only 50% confident that the prediction is true, you could probably drop it. Or if you want to have a higher threshold, you can do so as well. Okay? And this is repeated for all the properties that you are looking at. The last column is this value 1.064, and that is the log P, the predicted log P of avasivir, which is the lipophilicity. Lipophilicity is often written as log P. Now, this pretty much concludes all the 7 stages of drug sniffer. Now, in the past 2 hours or so, you've been typing so many different commands. You probably are tired, but I'll just push it for another 10 minutes and we should be done. Please stop. If somebody wants to run next. Okay, so Amit suggests that I stop here because we need to proceed with Daniel's lecture. So if you want to run next flow, which basically binds all of these, and you don't have to type in any of the commands that you've been doing for the past 2 hours, I would suggest you can simply copy paste the file, the tutorial files, and you should be good to go. All you need to then do is to supply 3 parameters, which is the database that you want to search. Now we have for the example purposes, we've created a very small database, but there is a bigger database that is downloadable from the drugsniffer.org website. That is quite a few gigabytes in size, so I would suggest you better have space on your machines before you download it. And you also need to specify what the receptor, that is your protein target is. Also specify what the pocket or the pocket position is, the pocket center. And you should be good to go. You can optionally decide whether you want to pursue admit. So all these are listed in a colored section, I think on page 4 or 5 of the PDF. Just go. Yeah, that's one. Yeah, so this is a simple example we have here for a different protein, 5L2S. You can simply replace 5L2S with 3VRI, but make sure that you change the center of the binding pocket to the exact coordinates that you just used just now. You also need to specify the dimensions of the grid that goes in X, Y, and Z directions. Decide which of the admit properties is relevant for your case. And you can decide also where you want to store the output of the run. And you can simply run the command. Oh, just before that, if you plan to run it today, I suggest that you first clone or just follow this command of cloning the drug sniffer repository. Do a CD to it, and then run drug sniffer inside the directory. Just make sure that you don't miss this dot, otherwise it's going to fail. And this is pretty much all you need to specify instead of the 40 different commands that you just sat down and wrote. This is the input file. Yeah. You don't need to copy it. It's already there in your drug sniffer directory. Yeah, so this is just to kind of tell you what it looks like. Yeah, you just need to modify this file and you should be done. So if you have a much larger database, we have a utility that we will provide later on where we can convert it into the format that we require. And that will allow you to do these similarity searches in much lesser time than what I showed in my slides, which were of the order of 30 seconds for even 100,000 set of molecules. We have searched over 3 billion in less than 2 minutes. Okay. Yeah, thank you. That's pretty much it. If you have any questions, do ask me. I'm still sitting there. Okay, thank you. Over to Daniel.
Okay, yeah.
Anybody hasn't for the steps, please come over there. We can help you out. We can help you out.
Okay, and we're going to take a 5-minute break while we get set up. So 3:15 approximately.
I'll move my laptop.